Namaste. Today we will study how to build input pipelines for TensorFlow. As you know, TensorFlow processes different kind of data sets. We have already seen couple of those kind of data sets in this course so far. One was the fashion MNIST data set. Apart from image data set, TensorFlow support text data. It also support structured data. It also supports other sequence data sets like time series data. So, you can see that the data sets are quite varied and their requirements are also quite different. For structured data, we want to pre-process the data by let us say normalizing it or by getting rid of missing values. In case of images, we might want to read images from multiple files on the system, and then we do image augmentation by rotating the images or by applying other kind of transformations on the image. In case of text data, we want to read the text data and we want to extract let us say tokens from the data by processing the text before we can use it in TensorFlow. Other important thing that we do in text data is to obtain embeddings for the words and convert words into integers or into some numeric data. So, the API for input pipeline building should be versatile to support all these kind of operations on varied data. Apart from the variety of structures, the data can be very big that it may not be possible to fit that data in memory, or data may be small data that can be easily fit in memory. So, this API also should support both these scenarios where it should be equally easy for the programmers to read data in memory as well as data that is sitting on the disk. So, tf.data API that is implemented by TensorFlow supports input pipeline building. It is a versatile API that supports all the requirements that we talked a few minutes ago. So, the tf.data API enables us to build complex input pipelines from simple reusable pieces. It makes it possible to handle large amount of data, different data format and perform complex transformations on the data. It introduces tf.data.dataset abstraction that represents a sequence of elements in which each element consists of one or more components. To take a concrete example of an image pipeline, an element might be a single training example with a pair of tensor representing image and its label. How do we create these data sets? There are two distinct ways of creating the data set. We construct the data set from data source, where the data might be stored in memory or it could be stored in one or more files. We can also perform transformations on one or more data set to get a new data set object. Let us try to understand basic mechanics of the data source and how to create the input pipeline from the data source. So, what we will do is we will first construct data source based on data that is in memory. We can use one of the two functions. One is from underscore tensors or from underscore tensor underscore slices from tf.data.dataset API. Alternatively, if our data is stored in TF record format, we can use tf.data.tf record dataset for reading that data. Let us construct a dataset from tensor slices. Here the data is stored in an array. There are 6 elements. Let us construct the dataset using from underscore tensor underscore slices function. You can see that the resulting dataset is a scalar because the shape is null and it stores integer 32 type of elements in it. Let us look at elements in the dataset. You can see that this particular dataset has 6 scalar which are integers, and these scalars or this dataset is constructed from this particular array. We can also use Python iterator for iterating over the dataset. We can use next function to get the next element in the dataset. So, here we show you the first element of the dataset, which is the number 8. Apart from creating the dataset from the data that is stored in memory or in files, we can also perform transformation on the existing dataset objects to obtain a new dataset. We can apply this transformation on every element in the dataset using a map function, or we can apply this transformation on multiple elements using a batch function. So, let us try to use a reduced transformation that reduces all the elements to produce a single result. To take a concrete example, what we do here is we take the data set that we constructed here and we reduce the data set to its sum. So, here we use a reduce function where we give the initial state which is 0, and then we define a lambda function on state and the value, where we add the existing state to the value and store the result into the state variable. So, as we go through the entire data set, the effect of this particular reduced transformation is to get us the sum of data set of integers. Let us run it and check the results. We can see that all the elements in this data source sums to 22, which is what is the output that we got here. Let us understand the structure of data set. A data set contains elements that where each element has the same structure and individual component of the structure can be of any type represented by tf.typeSpec. This includes sparse tensors, tensor array or dataset. Dataset.element_spec property allows us to inspect the type of each element component. So, let us check out the elements_spec of a data set here in a concrete example. So, here what we do is we construct a data set from tensor slices, where we have created a 4 by 10 tensor with random values from uniform distribution. Let us run this code cell to understand the element specification. We can see that each element in this data set is a vector or 1D tensor containing 1D tensor with shape of 10, and each value stored in this tensor is a float value. Let us construct another tensor, and here you can see that this particular tensor stores ordered pairs of two tensors. So, one is a scalar and second is a vector. We can zip dataset 1 and dataset 2 and inspect the element spec of the resulting data set. We can see that the resulting data set has element which is a pair of tensor, where the first tensor is a vector or 1D tensor with shape 10. Then we have a scalar followed by another 1D tensor with shape of 100. We store float values in first two tensors and integer values in the last tensor. We can also create a sparse tensor where we specify indices where there are values present in the tensor and provide the values in the values argument, and finally also give the shape, the dense shape of the tensor. Let us look at the element specification of this sparse tensor. So, we can see that we have a sparse tensor where the tensor is a 2D tensor with shape 3 by 4 and each element is a 32-bit integer. We can use value underscore type to see the type of the value represented by the element spec. So, we can see that in this data set 4 each value is a sparse tensor. The dataset transformation supports dataset of any structure. When using map and filter transformation, which apply a function to each element, the element structure determines the argument of the function. So, we can construct data set from different sources. We can construct it by consuming NumPy array or by consuming Python generators or TF record or by consuming text data or CSV data or by consuming bunch of files. So, what we will do in the next session is we will go through example of each of these data type and see how to construct a dataset object based on these different formats. Let us look at some of the operations on the dataset element. One of the important operation that we used during the training is batching. The simplest form of batching stacks n consecutive elements of a data set into a single element. We use batch transformation with same constraint as tf.stack operator. The batch is applied to each component of the element, and here there is a condition that all elements must have a tensor of exactly the same shape. So, let us see a concrete example of batching. So, here we construct two data set. One is INC underscore data set containing values between 0 to 100, and then DEC underscore data set containing values between 0 to minus 100. We construct a new data set by zipping both these data sets, and we construct a batch of 4 elements using batch transformation, and we call that data set as batched underscore data set. Let us iterate over batched underscore data set and see the elements in the batched underscore data set. So, you can see that since we have constructed batches of 4, we get from the INC data set we get 0, 1, 2 and 3 as the first batch of 4. From the DEC underscore data set, the first batch of 4 has 0, minus 1, minus 2, minus 3. The second element starts at 4 for the INC underscore data set, whereas for DEC underscore data set it starts at minus 4 and goes up to minus 7, and we print first 4 elements by using the TEC function and using 4 as an argument to the TEC function. We print first 4 elements in the batch. Let us try to change it to 5, and you can see that here we have 5 elements that are captured here, or the first 5 entries in the batched underscore data set are printed on the screen. While tf.data tries to propagate shape information, the default setting of dataset.batch results in an unknown batch size, because the last batch may not be full. So, we can check the shape of the batched underscore data set, and we can see that there is a none in the shape. We can use drop underscore remainder argument to ignore the last batch and get full shape propagation. So, let us say if we batch data set into a batch size of 7 and set drop remainder equal to true, we will check out the shape of the resulting batch. Now, we can see that the batch has a full shape, which is each element or each tensor is a 1D tensor with shape of 7. So, this particular recipe works for tensor that have the same size. However, there could be many models which might have varying size of tensors. To handle this case, we use padded underscore batch transformation. It enables us to batch tensors of different shapes by specifying one or more dimension in which they may be padded. Let us look at a concrete example. So, we construct a data set of elements between 0 to 100, and then we define a lambda function that repeats the element by the element time. For example, the number 1 will be repeated once, number 2 will be repeated twice, number 3 will be repeated thrice, and so on. And we apply padded underscore batch transformation on the data set. By specifying padded underscore shape and the number of elements in each batch, which is 4 over here. Let us look at the first two batches. You can see that in the first case, since the last element, which is 3, is repeated 3 times, we have padding of 3 applied on the first element, padding of 2 was applied on the second element, padding of 1 was applied on the third element. Look at the second batch has 7, which is repeated 7 times. So, each element from 4 to 6 are extended to shape 7 by padding the required number of zeros. So, the padded underscore batch transformation allows us to set different padding for each dimension of each component. It is also possible to override the padding value, which was 0 in the example that we just saw. Let us look at some of the training workflows with respect to the data sets. As you may be remembering that when we train neural network or any other machine learning model, we make multiple pass over the data set. One complete pass over a data set is known as epoch, and in mini batch gradient descent we use a small batch size to update the parameter value. So, what we need to do is we need to support the repeat transformation in the data set. So, data set has a repeat transformation that enables us to iterate over a data set in multiple epochs. Let us create a data set that repeats its input for 3 epochs. We construct a data set from a CSV file here. We define a function to plot the batch size to understand the effect of repeat and any other transformations that we will be applying. So, we apply repeat transformation with no argument to repeat the input infinitely. The repeat transformation concatenates its argument without signaling the end of one epoch and the beginning of the next epoch. Because of this, a dataset.batch applied after dataset.repeat will yield batches that straddle epoch boundaries. So, let us repeat the dataset 3 times and we process the dataset with a batch of 128, and let us plot the batch sizes. You can see that for different batches the batch size was constant, which was 128, except the last batch. So, you can see that we applied batch after repeat, and that causes the batches to straddle the epoch boundaries. Now, let us apply repeat after batch and see what happens. Now, you can see that when we apply repeat after batch, we can see incomplete batches after every 4 batches. So, you can see that here the batches are not straddling the epoch boundaries when we apply batch before repeat. In this case, it helps us to clear epoch separations. If we want to perform a custom computation at the end of each epoch, then it is simple to restart the dataset iteration on each epoch. So, let us say we want to print the shape of the batch and also print the epoch ID at the end of the epoch. We essentially do that in 2 loops, 2 for loops. The first for loop is for epoch, and within epoch we use batches on the data set. So, here we define epoch to be 3 and we construct a data set by batching the Titanic underscore lines data set into batches of 128. And you can see that there are first 4 batches with 128 examples in it, whereas the 5th batch has 116 examples. And you can see this happening epochs after epochs. Other important transformation is shuffle, and we have seen in some of the earlier classes that it is important to shuffle the training data to remove any systematic temporal biases that are present in the data set. So, dataset.shuffle transformation helps us to shuffle the data set. Shuffle maintains a fixed size buffer and chooses the next element uniformly at random from that buffer. The large buffer sizes shuffle more thoroughly, but they take a lot of memory and significant time to fill. In such cases, one can try interleave transformation across files, which yields the similar kind of effect as shuffle transformation. So, let us try to use the shuffle transformation on the Titanic data set. So, since the buffer size is 100 as you have defined it over here, and a batch size of 10 and a batch size of 20, the first batch contains no element with an index over 120. Let us check it out. Yes, you can see that the maximum value of the element in the first batch is 104. As with the batch transformation, the order related to repeat matters for batch. The shuffle does not signal the end of the epoch until the shuffle buffer is empty. So, a shuffle placed before a repeat will show every element of one epoch before moving to the next. So, here you have placed shuffle before repeat and we can see the elements. And let us look at the mean ID of the element. Now, what we do is we put shuffle after repeat and see what happens. There the item ID is near the epoch boundaries, and if you plot two graphs where we compare shuffle before repeat and shuffle after repeat. So, you can see that shuffle before repeat make sure that each element in the epoch is presented to the training data, whereas shuffle after repeat does not give us that kind of guarantee. So, depending on your requirement, you can either use shuffle before or after repeat. Another important step in data pipeline is pre-processing data, where we want to apply some function on each element of the data set. So, there are things like normalization or applying some kind of transformation on each element becomes an important part of data pre-processing. So, we use a map transformation for applying a given function or transform to each element of the input data set. We can also use map function to apply arbitrary Python function on each of the element of the data set. So, let us try to apply map on the image data. So, here what we will do is we will convert each image into a common size. To begin with, the images are in different sizes, we will convert them into a common size, so that they can be batched into a fixed size. Let us look at this transformation in the image data. We read images from a file, decodes it into a dense tensor and resizes it to a fixed shape. So, you can see that we first find out the label of the image, we read the image from the file, we decode the JPEG, we convert the image into float, and then we resize the image into 128 by 128 tensor. Let us apply it on the first image and see the result. We use imshow command to plot the image. So, this is the first image that is converted into 128 by 128 tensor. We apply it on couple of more images and you can see that the transformation converts each image into the same size, which is 128 by 128. We can also apply arbitrary Python logic using tf.py function. Note that for performance reason, it is better to use TensorFlow operations for pre-processing the data whenever possible. but sometimes it is useful to call external Python libraries, and this is where tf.py function helps us to perform map transformation. Let us look at a concrete example for this. So, here you want to use a rotate function from SciPy library. So, first we import the scipy.ndimage library, and we will be using the rotate function, and the image is rotated using the rotate function, where we provide the image, we provide the angle to rotate, which is decided randomly through a uniform distribution, any angle between -30 to 30, and it returns the image. Let us apply it on the first image and see the result. You can see that this particular tulip flower is rotated by, and you can see the rotated image of the tulip flower. Let us use this function with dataset.map. So, you can see that we use tf.py function to wrap the random underscore rotate underscore image function, and we call this particular tf underscore random underscore rotate image function, that in turn wraps the rotation function through py function. Let us see how this works on couple of images. So, you can see that both the images are rotated with different angles, chosen based on a uniform distribution between -30 to +30. Let us see how to use the data sets with high level APIs. There are two high level APIs, one is tf.keras and tf.estimator. We will first see how to use the dataset API with tf.keras. So, let us use a fashion MNIST dataset and build a sequential model or a neural network model through tf.keras.sequential. And here is we construct a dataset object for tensor slices of images and labels which are from the training set. Then we apply, then we shuffle the dataset with batch size of, then we shuffle the dataset with buffer size of 5000 and batch it into a batch of 32 examples. And we pass the training data set into the fit function and provide epochs for which we want to train the model. If we pass an infinite data set by calling repeat without any arguments, we need to pass steps per epoch along with repeat, where we do not specify any argument for repeat. Here, if we want to evaluate accuracy on the training set, we pass the training data set to the evaluate function. If our data set is big, we set number of steps to evaluate. Here we set number of steps to 10. So, the effect is that we get the estimation on the estimation of performance of the model on the training set on a sample. So, the labels are not required while calling model.predict. Even if we pass a data set containing label, the labels are ignored by the predict function. In case of TF estimator, we need to define input underscore function that returns a dataset object, and then the framework will take care of consuming its element for you. So, if you want to give Titanic dataset as input to TF.estimator, we define train underscore input underscore function, where we create a Titanic dataset and perform transformations like repeat and shuffle. And we also specify the prefetch so that the batch is fetched before time, so that the training is not stalled. In addition to that, you have to convert the non-numerical columns into numerical columns. For example, categorical columns have to be converted into numbers either using hash buckets or vocabulary list. And then in the train function of the estimator, we specify the input function. We can also specify the input function in the evaluate function to get the evaluation results. We can get the predictions for each of the example in the training by running a predict function on the estimator by specifying the training input function, which consumes one element at a time and gives the predictions for each of the element. Here we print the prediction for the first element, after which we break. So, in this session we studied how to build input data pipelines with TF.data API. In the next session we will learn how to construct TF.data set from different formats like CS, text data and image data. Hope you had fun learning concepts behind creating input pipeline for TensorFlow. See you in the next session. Dhanyavad.